Let's go.
Hi, my name is Nandish AS. I am going to explain two DDCO lab programs today. The first one is fifth lab program, that is Design Verilog HDL to implement decimal adder. This is about how to implement a decimal adder using Verilog HDL and analyzing output. Now we can see how it goes. The Verilog program is module decimal adder a comma b comma sum input 3 is to 0 a input 3 is to 0 b output 4 is to 0 sum assign sum is equal to a plus b end module. Explanation for this Verilog program. The first line module decimal adder a comma b comma sum. This line defines the module named decimal adder. The module takes three parameters, that is two inputs a and b. We can see two parameters a and b is taken and one output, that is sum. Here we can see sum as a parameter. The second line, input 3 is to 0 A. This line declares A as a 4-bit input. The 3 is to 0 indicates a 4-bit width for the signal. This means it can hold binary values from 0000, that is 0 in decimal, to 1111, that is 15 in decimal. Input 3 is to 0 B. Similar to A, this declares B as another 4-bit input. Fourth line, output 4 is to 0 sum. This line declares sum as a 5-bit output. Since the addition of two 4-bit numbers can result in a maximum value of 1111, that is 30 in decimal, so we require 5 bits to store the result. Fifth line, assign sum is equal to a plus b. The assign statement performs a continuous assignment. Here, sum is assigned the result of adding a and b. This operation will be performed automatically whenever a or b changes. Sixth line, end module. This marks the end of the decimal adder module definition. Here, this is the image for four selected signal. Now we see what happens. The images show a test of the module in a simulation tool. Here's what they indicate. These dialog boxes show the assignment of values to the inputs A and B during simulation. Four selected signal, input A and B. Both the values are entered as unsigned decimal. Here we can say in value radix, it is unsigned decimal, and here also unsigned decimal. For example, A is set to 6, that is in binary 0110. Here we can see forced to value, that is 6 for A. B is set to 9 in binary, that is 1001. Forced to value here is 9. The in binary it is 1001. Here is the output for fifth lab program. Now we see waveform analysis of it. The lower part of the image shows a waveform view of simulation. Here's how to interpret it. A 3 is to 0 displays the binary value of A. Example 0110 for decimal 6. Here A 3 is to 0 having value 0110 has 4-bit value, and B 3 is to 0 displays the binary value of B. Example 1001 for decimal line 9. B 3 is to 0 is a 4-bit input that contains value 1001, that is equal to 9. Sum 4 is to 0 displays the binary result of A plus B. Sum 4 is to 0 has a 5-bit output that contains the value 01111, that is 15. Here we can see for A is equal to 6 and B is equal to 9, the sum of both A and B is equal to 15, that is binary 0111. Here we can see the value 01111. This is the end of the fifth lab program. Thanks. Now I am going to explain sixth lab program, that is design Verilog program to implement different types of multiplexers like 2:1, 4:1 and 8:1. First of all, what is a multiplexer? A multiplexer is a combinational circuit that selects one of many input signals and forwards the selected input to the output based on the value of the select lines. There are many types of multiplexer. Some of them are 2 is to 1 multiplexer. It has two inputs and one select line. 4 is to 1 multiplexer. It has four inputs and two select lines. 8 is to 1 multiplexer. It has eight inputs and three select lines. Now we are going to check the Verilog program for 8 is to 1 multiplexer. The Verilog program is as follows. Module mux s comma d comma y input 2 is to 0 s input 7 is to 0 d output y reg y always at s or d case s 0 is to y is equal to d of 0 1 is to y is equal to d of 1. Similarly, up to 7 is to y is equal to d of 7. End case and end module. The explanation for this is the first line module mux s comma d comma y. This line defines the module named mux. The module takes three parameters, two inputs that is s and d and one output that is y. S stands for select line, D stands for data inputs and Y is for output. The second line, input 2 is to 0 S, defines a 3-bit wide input S that will be used to select one of the 8 data inputs. Third, input 7 is to 0 D defines the 8-bit wide data input D, where each bit corresponds to a different data option. Output Y declares a 1-bit output Y that will hold the selected value from D. Reg Y assigned inside an always block. It must be a reg type. The sixth line, always set S or D, ensures that the output Y updates immediately whenever there is a change in the inputs of S or D. This is required for combinational circuits like multiplexer, where the output must always reflect the current inputs. Case S. This starts a case statement that checks the value of the selector S. It executes the corresponding branch based on the value of S. 8. 0 is to y is equal to d of 0. If s is equal to 0, 0, 0, assigns the value of d of 0 to y. Here we can see y has been assigned for d of 0. 1 is to y is equal to d of 1. If s is equal to 0, 0, 1, assigns the value of d of 1 to y. Here we can see that d of 1 is assigned to y. So on for all cases up to s is equal to 1, 1. It continues till 7 where d of 7 is assigned to y. In ninth line end case, this ends the case block. 10th end module, this ends the Verilog module. The output for 8 is to 1 multiplexer is here S of 2 is to 0 is having the 3-bit select line having the value 1 1 1 and D of 7 is to 0 is having a 8-bit output input having the value 0 1 1 0 1 0 1 0. Y is having a 1-bit value that is 0. Here the output for S of 2 is to 0 for 1 microsecond is 000, 2 microsecond is 001, 3 microsecond is 010, 4 microsecond is 011 and 5 microsecond is 100. For D of 7 is to 0, the output will be same for all the microseconds 011011010. Now we have to go through the 4 is to 1 multiplexers Verilog program. Module mux s comma d comma y input 1 is to 0 s input 3 is to 0 d output y register y always set s or d case s 0 is to y is equal to d of 0 1 is to y is equal to d of 1 2 is to y is equal to d of 2 3 is to y is equal to d of 3 end case end module. This is similar to the 8 is to 1 multiplexer but which only have a 2-bit selector and a 4-bit data input D of 3 is to 0. The case statement checks the 2-bit selector S and assigns the corresponding data from D to Y. The output is is S of 1:0 is a 2-bit selector having the value 1 and 1, and D of 3:0 is a 4-bit data input having the value 1 1 0 0. Y is a 1 bit having the value 1. The output for S of 1:0 will be 0 0 0 1 1 0 and 1 1 for each microsecond. For D of 3:0, that will be same for all microsecond 1 1 0 0. Now we move through the 2:1 multiplexer having module mux s comma d comma y. Input 0:0 s, input 1:0 d, output y. Reg y always at s or d. Case s, 0:y is equal to d of 0, 1:y is equal to d of 1. End case, end module. This is the simplest multiplexer where S is a 1-bit selector and D is a 2-bit data input. The case statement checks will assign either D of 0 or D of 1 to Y based on the value of the selector. The output is S of 0:0 is a 1-bit selector having value 1. D of 1:0 is a 2-bit data input having the value 0 and 1. Y is output having a 1-bit value 0. The output for S0:0 is for 1 microsecond it will be 0 and 2 microsecond will be it is 1. It is based upon the value of the selector. D of 1:0 is 0 1. It is the end of the sixth program. I hope you have enjoyed this. Thank you.
By using this simple Verilog program, we can understand about the demultiplexer. Module Dmux. Dmux is the module name. S is the 2-bit input signal that acts as a select line, and D is a single bit data input, and Y is a 4-bit output vector. It represents the 4 possible values output of the demultiplexer. Here input S, input D, output Y. It represents S is a 2 bits wide to allow the 4 combinations 0 0 0 1 1 0 1 1, and input D it is a single bit input data signal that is forwarded to one of the output. Here we are registering the value of Y. It is a 4-bit wide register initialized to 0, where only 1 bit is activated based on the select pin. Here the always block is triggered when there is a change in the select pin or the input. Then begin. Y of 3 of 0 equals 0 is initialized. It ensures that the all outputs are reset to 0 before setting the appropriate list. Next case statement is given. Case yes, it evaluates the value of select pin. Depending on the value of S, these are the cases given. If Y of 0 is set to D, if S equals 0, if Y of 1 is set to D, if S equals 1, Y of 2 is set to D, if S equals 2, Y of 3 is set to D, if S equals 3. Only one output will be D and the rest will remain 0. Here end case is the end of the case, and end module. This concludes the Dmux implementation. Output for this is like this. Here S of 1 of 0, it represents the select line. It determines which output line will receive the value of D. It is a 2-bit input with possible values 0 0 0 0 0 1 1 0 1 1. Here 0 0 is the value, and D is the data input. It is a single bit input. It and routed to one of the Y of 3 of 0 output based on the value of S. Y of 3 of 0, it is a 4-bit vector where only 1 bit will be 1 at any time and others will remain 0. The active bit corresponding to the value to the select line S of 1 of 0. it is 0 0. In timing diagram, we can see that from 0 to 1 microsecond, S is ZZ. It indicates the uninitialized or high impedance state for select pin, and D equals XXXX, showing uninitialized value for D. Y of 3 of 0 is remains undefined during this time. From 1 to 2 microsecond, S equals 0 0. The select line points to Y of 0, and D equals 1. The data input value is 1. Y of 3 of 0 equals 0 0 0 1, meaning Y of 0 is active and all others are 0. From 2 to 3 microseconds, S equals 0 1. The select line points to Y of 1. D equals 1. The data input value is still 1. Y of 3 of 0 equals 0 0 1 0, meaning Y of 1 is active and all others are 0. From 3 to 4 microsecond, S equals 1 0. The select line points to Y of 2, and D equals 1. The data input will remains 1 only. Y of 3 of 0 is equals to 0 1 0 0. That it means Y of 2 is active and all others are 0. From 4 to 5 microsecond, here S is initialized as 1 1, and it corresponds to Y of 3, and D is here also D equals 1. Y of 3 of 0 is equals 1 0 0 0, meaning that the Y of 3 is active and all others are 0. For implementing various types of flip-flops such as SR, JK, and D. First we will take about the D flip-flop. Here is the Verilog code. Module DFF. DFF is the module name, and D is the data input, and Q is the main output, and QB is the complementary output. CLK is the clock signal, and RST is the reset signal. Here input is D clock signal and the reset signal. Output is Q, QB. Q and QB are declared as the register because their values are stored across the clock cycles. QB is complemented as the complement of Q. Here in always the always block is triggered on the rising edge of the clock. This ensures that the D flip-flop updates its output synchronously with the clock. Here it is we have to begin. If RST of Q is less than or equal to 0, it means if the reset signal is high, the flip-flop output is set to 0. This is a synchronous reset, meaning it occurs only on the rising edge of the clock. Otherwise, here begin for the cases. Here is the cases for the D flip-flop. If RST is not active, the flip-flop process the input D. When D is equals to 0, the output Q is set to 0. When D equals 1, the output Q is set to 1. This behavior matches that of a D flip-flop. The output Q follows the input D on the clock's rising edge. And we are ending the case here. Next, we are assigning QB, that is complementary output is equal to inverse of the Q. This ensures that QB is always a logical opposite of the Q. And we are ending the module here. This concludes the module implementation. Output for this is given below. This is the output of the D flip-flop. Here D represents the data input, CLK is the clock signal, RST is the synchronous reset, Q is the output and QB is the complement of Q. Uh, the output Q is set to 0. The output takes the values of D on the rising edge of the clock. QB is always a complement of Q. This waveform shows how Q follows the value of D synchronously with the clock. Now let us know about the JK flip-flop. Here module JKFF is the module name. J is the set input and K is the reset input. Q is the main input and QB is the complement of Q. CLK is clock signal and RST is the reset signal. Here we are assigning input as J, K, clock, reset signal, and output are Q, QB, and we are registering Q, QB. And the always block is used and it is triggers on the rising edge on the clock. This ensures that the JK flip-flop updates its output synchronously with the clock. And we are beginning here. If the reset signal is I, the output Q is set to 0. This is a synchronous reset, meaning it occurs only when only on the rising edge on the clock. Otherwise, here some cases are there. We are beginning the case here. Case J, K. The concatenation J, K creates a 2-bit vector based on the J and K. The cases handle different input combination. If it is 0, 0, there is no change. The output 0 remains in its current state. If it is 0, 1, the output Q is set to 0. If it is 1, 0, the output Q is set to 1. If it is 1, 1, the output 0 flip its state. 1 becomes 0 and vice versa. And we are ending the case here. And we are ending this begin. And we are assigning QB is inverse of Q. That is QB is the complementary output and Q is the main output. It continuously updated to reflect the logical opposite of Q. And we are ending this begin. And we are ending this module. This marks the end of the module definition. And the output for JK flip-flop is given here. Here J and K are the inputs that control the flip-flop behavior. CLK is the clock signal. It is used to trigger changes. RST is the synchronous reset to clear the flip-flop state. And Q and QB are the, here Q is the main output, QB is the complement of Q. If RST equals 1, the output Q is set to 0 and the QB is set to 1. If J equals 0, K equals 0, no change in the Q. If J equals 0, K equals 1, reset Q equals 0. If J equals 1, K equals 0, set Q equals 1. If J equals 1, K equals 1, next toggle Q flips its current state. This waveform reflects this transition, showing how Q and QB change on the rising edge of the clock based on the values of J and K. Here, if Q is 1, then QB equals 0. If Q equals 0, QB equals 1. Thank you. Now let us see about the SR flip-flop. Here the module SRFF. SRFF is the module name. And S is the input, R is the reset input, and CLQ is the clock signal. RST is the reset signal, and Q and QB are the Q is output and QB is the complement of the output. Uh, Here input is S comma R comma clock signal comma reset signal. Output is Q comma QB. Uh, we have to register Q and complement of Q is that is QB. Here the always block is triggered on the raising the edge of the clock. This it ensures the SR flip flop update its output synchronously with the clock. Next we are beginning here. If reset signal is high, the flip flop output is set to 0. This is the synchronous reset, meaning it occurs only on the rising edge of the clock. Otherwise, we are beginning, and so these are the some of the cases. S comma R, it is a concatenation of the set and the reset input, which results in a 2-bit value. If it is 0, 0, there is no change. The flip flop holds its current state. If it is 0, 1, reset, the output Q is set to 0. If it is 1, 0, set the output Q is set to 1. If it is 1, 0, the output Q is set to 1 again. If in some condition it will be invalid state, both S and R being 1 is not allowed in a SR flip flop. So the output Q is undefined state, and we are ending the case here, and we are ending as we have begun here. Now we are assigning QB is equal to complement of Q. This ensures that the QB is always reflect the logical opposite of the Q. And we are ending here, and we are ending this module. This concludes the module implementation. The output for the SR flip-flop is as follows. Here S and R are the inputs for the set and the reset. CLQ is the clock signal for the synchronous operation. RST is a synchronous reset. Q and QB here. Q is the output and QB is the complement of Q. Reset active is equals to 1. The output Q is set to 0. Inputs are S comma R. If S equals 0, R equals 0, then there is no change. If S equals 0, R equals 1, reset Q equals 0. If S equals 1, R comma R equals 0, set Q equals 1. If S equals 1, R equals 1, it is an invalid state. The waveform reflects how the output changes on the rising edge of the clock based on S and R.